Right, hello everyone. I will now present my findings in Senior Mechanical Lab for thermodynamics, heat transfer, and fluid mechanics. For thermodynamics, it is to determine heat capacity of water. For heat transfer, it's to prove concept of cooling towers. Fluid mechanics is to prove Bernoulli's principle. So for the initial setup, I will do it, and for heat transfer, Alvin did it, and for fluid mechanics, Glenn did it. For each week, the module rotates from person to person. So for example, in thermodynamics, since that I'm the one who did the initial setup, uh, I will also do the experiment first, and then I will ship it to Glenn. Glenn does the experiment and ship it to Advent. Same for heat transfer, the cycle is the same. So Advent send it to me, and then I will send it to Glenn again. For fluid mechanics, Glenn send it to Advent, and then Advent send it to me. Now, for the components of thermodynamics, I will need two styrofoam boxes, one smaller than the other. And I found these boxes in my garage. I will also need an immersion heater, which I bought online for under 3,600, including shipping. Thermometer, which costs 49,700, includes shipping as well. A tape, and my phone as a stopwatch. For heat transfer, we need two large buckets, some wooden skewers, another basket, two funnels, two tubes, two jugs, two thermometers, cardboard, and phone as a stopwatch. For fluid mechanics, we need a barrel, pipes, water stopper, valve, measuring tape, and pipe sockets, and phone as a stopwatch. In total, it costs 717,300 for all three modules combined. Now, for the assembly for thermodynamics, make two holes for the lid at a small box and insert the thermometer and the heater into it. And make sure to tape the remaining gaps so water does not escape through evaporation. Now at the side of the larger box, here, cut a slit so that the cable can exit the box so that it can connect to the power outlet. Now for the experiment, we put water up to 5 centimeters so that we can take the volume of the water, and from the volume we can find the mass through the density. Next, close the lid. Make sure that the heater does not touch the box, because there might be a possibility that the heater can melt the box since the box is made from styrofoam. Now put the smaller box into the larger box and then close the lid. Then connect the heater to a power outlet and to take the temperature of the water every 3 seconds up to 300 seconds. Make sure to close the lid after taking the temperature. Now, assuming that the system is adiabatic, so that energy in equals to energy out. So in the heater, it will be electrical power going in. So power times time equals to the heat of water, which is mc delta T. We can find C by making it as a subject, so PT equals to m over mt. Now, I have found the temperature after each 30 seconds increment, and as a comparison, the specific heat capacity of water is 4,180 joule per kilogram Kelvin. And as you can see as well, the percentage error is quite large and might double the value of the specific capacity of water. So therefore, we can see that this system is not exactly accurate in finding heat capacity of water. So as a conclusion, we can say that this system is not accurate. This may be due to the assumption that the power supplied into the heater is constant. We don't know that, since that we cannot control the voltage or the current going into the heater. There's also might be a possibility that there's a heat loss out of the system, since that this is not an exactly isolated system. And moving on to the heat transfer. For the assembly, since Alvin did it, all I had to do is just to place 2 book binders over the large bucket and place the cooling tower, which is this contraption over here, onto the binder. Attach funnels into tubes. So here's the funnel and here's the tube, and heat the water and divide it into jugs equally. So the jugs here and here contain hot water. Honestly, I forgot to take a picture of my setup, so I've got to borrow the setup from Advance. It's exactly the same, however. So for the steps, take the initial temperature of the hot water in the jug, and then pour the water into the funnel slowly. Wait until all liquid drops or flows into the bucket, and then measure the final temperature of water. So the way that the cooling tower works is that the hose in the bucket allows the air to enter the bucket so that it can cool the water through convection. Now the hot water in the control setup, the one that has no cooling tower, or the pipe, or just the pipe that is going into the bucket, has less chance to cool down since that it's flowing through a closed tube. So the initial temperature for the cooling tower jug is 71 degrees Celsius and the control is 68. The final temperature is 46 to 54, and we can see that the cooling tower cools more than the one in control setup. So we can conclude that convection cools water effectively and the cooling tower works. And now we can move on to fluid mechanics. So for the assembly, attach the valve into the hole of the barrel. So we can see that is here. Attach all of the 3/4 of an inch of pipes into the valve and level off the pipes horizontally. And this is the only assembly that I have to do since Glenn did the previous setup. Now for the experiment, measure the length of the pipe from valve to the end. So from this point here up until this point here. Fill water into the barrel up to 10 cm above the valve. Open the valve and let the water out. Measure the time taken and repeat steps 3 and 4 3 times. But when repeating the steps, make sure to wait all of the liquid to flow out of the pipe so that we can see that when we stop the timing, we can see that that's the actual water flowing and not the residual flow. Then repeat 3 or 4 times, but fill the water up to 20 centimeters above the valve. Now this is to prove that the velocity of liquid due to gravity is square root of 2gh, where g is the acceleration and h is the height of water. And that velocity has to be the same with the velocity of the pipe, of the water flowing into the pipe, which is length over the time. Now, the higher the water level, the fastest it can go since it carries more potential energy. Now, for the water level at 10 cm, the velocity by using Bernoulli's principle is 0.443 meters per second. Now, when I take the time, it's about 3.1 seconds and 3.4 seconds, and the percentage error from there is 33 and 21%. When the water level is at 20, I can see that the time is shorter, which means that the water flows faster, but the error percentage stays somewhat the same except for one outlier reading, which is pretty accurate. So we can see that the speed of water at the 20 centimeter water level is faster, and this setup is actually pretty accurate at measuring water flow. However, there may be sources of inaccuracy due to the pipe not being exactly horizontal. The surface of the pipe is not perfectly smooth, so we have to take in consideration of friction and also the reaction time when timing the water flow as well. So, as a feedback of Senior Mechanical Lab, it is fun since I find it fun since it challenges my creativity because I've got to perform experiments with traditional household items as opposed to the equipment that we get from labs. And also I've got to improvise when equipment is missing or damaged during shipping, because for instance during fluid the experiment for heat transfer, we have a missing book binder, so we have to balance the cooling tower by hand, which is tedious. And also one annoying thing for me is that my water fee will be very expensive this month because I've used up a lot of water this lab. Anyway, that is the end of my presentation. Have a good day.